Okay, so this video is to try and illustrate the basics of and different types of antennas, polarization, gain, patterns, and so on and so forth. Now, before I go any further, although my background is electronic engineering, I don't claim to be a professor in the subject. So the idea of this video is to try and help you visualize the concept of the different types of antennas, how they interact, and what some of the terminology is. Because I feel a lot of the sort of subject matter out there regarding the issue is a little bit technical, a little bit geeky, and unless you've got a background in RF, it's sometimes a bit hard to explain. So I'm going to try and put it in layman's terms, and I'm going to try and do this in 3D to try and help you visualize what's actually going on with the different types of antennas. Now, every antenna has a different pattern, and we're using here a 2 decibel omnidirectional rubber ducky antenna. Now, this is like your typical antenna that you get in the box when you first buy your your standard antenna when you get your transmitter and receiver. So everyone should be familiar with this antenna. Now, the pattern is usually available from the specifications that you get when you're buying your antennas. So this one here, for example, we see the vertical, which assumes that you're looking from the side and you take a cross-sectional slice from the side, and that's how the radiation pattern, how it's radiating from the center of the antenna. And likewise with the horizontal, we assume we're looking from above, and we again take a cross-sectional view, and that's the typical pattern of that antenna. So to better visualize that a little bit better, what we'll do is we'll show you it in 3D. So now this is, the Omni antenna is mounted on the wing, and we're mounting it vertically. Yeah. Now, some people like to mount theirs horizontally, i.e. sticking out the side of the wing, which is fine, but for the purposes of this video, we'll keep it consistent. We'll assume that we've mounted our antenna vertically at the top of the wing. So let's deal with the gain first. Now, a lot of people think the gain represents some sort of strength or the sensitivity of the antenna. And what it really is it determines the pattern. And you have high gain and low gain antennas. Now, a 2 decibel omni antenna like this would be a low gain antenna. The benefit with low gain is the pattern is very all the way around it. The field of view, if you like, is extremely wide. And with an omnidirectional, it's in all directions around it. So let's have a look at the typical pattern for this particular antenna, which we'll start with, and it looks like that. So, and again, this is taken directly from the specifications, and a 0 dB decibel gain antenna would be a perfect sphere. So in all directions it would be a perfect sphere. Now this is 2 decibels, so there are areas of sensitivity that are lower than others. And you'll notice at the top here we've got a void, and likewise at the very bottommost part of the antenna there is also a void. And again, at the angle we're looking at, let's just turn that one off so we can see. That's how it's emanating. Now you'll notice that these sections are oriented vertically. Now, this antenna is a linearly polarized antenna. It's linear polarization, which means it's either vertically or horizontally polarized. Now, that just is controlled based on how we've mounted it. Now, because we're mounting it in a vertical orientation, we therefore have a vertical polarization pattern from the transmission. So this is our plane, and obviously we have the same antenna on the ground station. I'll switch to the front view, which is actually the side, but we'll call it the front. So on the ground station we have a rubber ducky 2 down here. So this is again, this is a typical rubber ducky again on the ground station. So let's turn on the pattern for that. looks the same, exactly the same antenna, so therefore we have the same pattern. Now, and again I'll flick to the front view for this. We'll assume that here's your plane, we fly around the sky. Assuming that the plane pattern is touching the ground station, we're in range. If there's a gap between them, we're out of range, and therefore we're getting an awful lot of interference, or if any video at all. So assuming they're touching, we're in range. Now, if we look from the top view, you will notice, and again, here's your plane. These are both vertically oriented antennas. The polarizations match, and the benefit with that, as you can see, is this cross-sectional area here where they join up is extremely large. Yeah, they're sharing an awful lot of the same space, which means we're going to have a very, very good signal. So the benefit with the omnidirectional antenna, the low-gain antenna, is that it emanates from every direction around it. So as we fly around our local flying field, regardless of where we are in the sky, you're always going to have an area that's matching up beautifully and shares a very large cross-sectional area of the radio waves joining up. Yeah. So whether we're beside us or behind us, we're always going to have a very good link. However, the range is never going to be brilliant, but there's always a payoff. So we can only come this far before we start losing a signal. But the benefit is we can fly in any direction around us and we'll get a good signal. So that's in a perfect world. However, because of the nature of obviously how we fly planes, etc., we'll turn off the pattern on the plane for this illustration. But the problem starts to arise as to when we're flying around, this is all brilliant, we're in perfect straight and level flight. But when we start going into a turn and banking, what we find is that in fact now, if I switch to the plane cam, we're actually no longer in vertical orientation. The plane is now mounted horizontally. Now, as a result of that, as is now our signal. Now, regardless of the fact that what we'll do is we'll switch back to the front view. There's our plane in a hard turn. Now, just because our plane is in range doesn't mean we're going to get a good signal, because we've got a mismatch of polarization here. One is vertically polarized, the ground station, but the plane is now horizontally polarized. So what it means is that we have a mismatch of polarization. This mismatch will cost us about 26 decibel of gain loss, which is significant, yeah? And what you'll notice is that here, this is our cross-sectional area that's matching up, yeah? And if you were to measure this wafer-thin cross-sectional area, plus this bit, plus this bit, plus a little bit here, a little bit there, it's tiny in comparison to how it is when obviously these two are matched up in their orientation. And again, if we look from above, we see that shared cross-sectional area is massively larger, so that loss of gain when we mismatch the polarizations can be extremely costly in our range, and you get a massive amount of interference. Now, it's not the end of the world, because there are things that we can do, and this is the idea of diversity antennas, for example. So here's our plane. We'll leave the radiation pattern on that for clarity. We'll turn off our rubber ducky antenna, and let's have a look at a typical diversity antenna. Now, we're all familiar with the panel-based antennas. Now, this is a diversity antenna, which is 11 dB, so it's 11 decibel gain versus the 2 decibel for the rubber ducky. Now you'll notice they have two cables coming out of the diversity antenna, because it's actually got two antennas built inside rather than one. So this is a flat patch 11 decibel gain. So let's have a look at the pattern for that. Let's go for BAM. So as you can see straight away, what we'll do is we'll move the plane out of range for the time being. What we can see is that it's a cone shape. Yeah, so if we compare that to the rubber ducky antenna on the ground, this is our central point here. So we're forward facing. There's nothing around the back for the diversity antenna. So there's no good flying behind it or above it. So one of the downsides is that it's a much narrower field of view, meaning we need to make sure the antenna is pointing very specifically at the aircraft. So in terms of how the, let's switch to the diversity pattern camera. So again, this is one of the antennas built inside the diversity antenna, which is the vertically polarized one, because again, our segments are running vertically in the same orientation as our antenna on the plane is running. So this is an ideal scenario. So assuming the plane is in here, we of course have a nice cross-sectional area being shared between the two. So again, that's all very well, but let's assume again our plane is in a turn. So we're doing a hard bank again in the plane, and we still have the same problem of the mismatch of polarization. However, because it's a diversity antenna, not only does it have the vertically polarized antenna built in, but there is also a horizontally polarized antenna. It's exactly the same as the vertical one, it's just mounted at 90 degrees. So we can turn off the vertical one, and so this is how it looks for that. Again, it's about a 50 degree field of view, but the antenna is mounted internally at 90 degrees, giving you horizontal polarization. So this is linear diversity. There's a diversity between the polarizations essentially. So again, as we turn into a turn, the horizontal polarized antenna is going to be the one that your receiver chooses because it's got the biggest cross-sectional view. And that's all a diversity receiver does, is it looks at both of the signals coming in from each of the receivers and chooses the one that's strongest and switches to the one that's getting the best signal. So in this instance, the horizontal antenna is getting the best reception because our plane happens to be in a horizontal fashion. So let's return the plane back to straight and level flight. And again, we see we've got a mismatch here of polarization. But of course, let's turn both of the patterns on that we've got with our diversity receiver. This is the benefit look. You've got both vertically and horizontally polarized antennas in one. So regardless of your orientation, you're always going to get a good signal, whether you're in a hard turn or vertically going up towards the moon. You're going to get a brilliant signal. What you'll also notice, of course, if we turn on and compare the ground-based rubber ducky pattern, is the range look. We'll just switch back to the side view. So this is where you're going to get to with your rubber ducky. However, with a diversity receiver, because it's a higher gain, 11 decibel, versus 2 decibel of the rubber ducky, we can get right the way out here. So not only do we get a greater range, but we also have a more of a consistent signal, because regardless of our orientation on the plane, whether it's vertically or horizontally, the diversity antenna will be able to pick up a good signal. So that's your typical diversity antenna, 11 dB pattern. Let's turn that one off. So again, we've got our plane flying around the sky. The other one we've got is a circularly polarized antenna. And a popular one is the 8 decibel circularly polarized antenna. And from the side, this is how it looks. So this is a circularly polarized antenna, 8 decibel. Now, for this to be theoretically correct, this would be a corkscrew shape, but we're keeping things simple. This is to illustrate, nothing more. So now, circularly polarized antennas are brilliant. They seem to have a much more resilient signal in terms of going through foliage and trees and obstacles compared to that of a linearly polarized antenna, such as the Diversity or the rubber ducky. Now the downside is that obviously we're not transmitting a circularly polarized signal. We're transmitting, in this case, a vertically oriented signal. So there's going to be a loss because we have a polarization mismatch here. One's circular, one's vertical. However, the great thing about a circularly polarized antenna is that your loss, instead of it being 26 decibel, remember, from if you've got a horizontal antenna trying to talk to a vertical antenna, you've got a 26 dB loss, which is massive. However, the linear, as in vertical or horizontal polarization versus a circular mismatch, is only 3 decibel. And the great thing is that with a circularly polarized antenna, because of the way it works, you're never going to get less than 3 decibel loss, no matter what your orientation is on the plane. I mean, if we look at the actual cross-sectional view here, when you look sort of directly at the circular antenna, yeah, this area here is almost like a vertical cross section, as is from the top. This here is almost a horizontal cross section. Now it's not perfect, so again we've got that loss, but the great thing about the circularly polarized one is that it's very consistent. And assuming you're keeping yourself within the range, you're going to have a very good signal. And again, remember we're on a patch antenna here, yeah. So and because it's 8 decibel, it's not omni, yeah. So we have to make sure that we're pointing the 8 decibel circular antenna at the aircraft. It emanates from the face of it. So, there's no good flying behind us or anything. It won't pick you up. But if you're in this vicinity in front of the circularly polarized 8 decibel antenna, you're going to get a rock solid signal no matter where you are around it, despite that 3 dB loss. Because again, if you compare that to the linear differential, that's 26 decibel loss, yeah. So, if we compare the range, which is always an important factor, this is your rubber ducky, and again we would only get to about here, but with the circularly polarized we're going to get a little bit further out because we're 8 decibel versus 2. But obviously the same problem exists. We can't, with the rubber ducky we can fly behind and we're all good, or we can fly in front only in the field of view of a circularly polarized. So let's turn off the ground station antenna. So let's compare that to the Diversity antenna, which, we're talking 11 decibel versus 8. So it's slightly higher, so we're getting a little bit further out, but again, with the circularly polarized, it's a much better signal through trees and in your local vicinity. So that's your circularly polarized antenna. Now, going high gain antennas, let's turn off the circularly polarized one. Quite a popular high gain antenna. I mean, it's not much difference between a patch antenna and a Yagi, but we're going to look at the Yagi, which is, we'll turn off the Diversity antenna. Yagi is like a tube, yeah. And if you compare that to your rubber ducky antenna, So it's like a tube. These can be up to 2 meters long if you get extremely high gain. But we're going to base this on the 15 decibel Yagi antenna. So remember, the diversity was 11, the circular was 8, and the rubber ducky is 2. So this is your Yagi, which is 15 decibel, which is about half a meter long. So let's have a look at the pattern for a Yagi. Now remember, because it's very high gain, we get an even narrower field of view. Let's turn on our let's turn on the Yagi. Bang. Yeah. So you can see this is only about 30 degrees field of view here. So this is even more important, that you make sure that this antenna is pointed directly at your plane. Yeah. And again, this is a linearly polarized antenna, i.e. it's either vertical or horizontal. So if we look from the top, we can see the pattern here is in a vertical fashion. So, you know, as long as we maintain this range and orientation, we've got a brilliant signal. And not only that, the range is significantly higher. So again, here's your Yagi range. We're all the way out here, look. And let's compare that to the diversity antenna, which is pretty good range. Let's get the pattern on for that. Is here, yeah. So we can get to about here with your diversity, 11 decibel. We can get all the way out to here with your 15 dB Yagi. So the downside, of course, is that the field of view is not quite as good. So with the diversity receiver, 11 decibel, I can be flying here and get a pretty good signal. But with the Yagi, I'm out of range here, look. And again, behind it, forget about it. It's not even going to know you're there. Yeah, above it. You have to be very, very specific about where you're pointing your Yagi. Now, this is the main reason why the antenna trackers have become so popular. Because what it allows you to do is to use these high gain antennas that have got a very narrow beam and sensitivity pattern. But obviously the benefit of the antenna tracker, what is it? It will always keep it pointed at your plane. So you can get great long range, not have to worry about, you know, making sure it's pointed exactly in the right position. So we still have the same problem though, remember. We still have the, you know, we've still got the problem of the linearity of it, yeah? It's either vertically or horizontally polarized. So again, one of the ways we can get around that is to have the best of both worlds. So for example, we can have our Yagi that's vertically polarized, and we can have another Yagi which is horizontally polarized right next to it, yeah? So two separate Yagi antennas just rotated 90 degrees from each other will give us the same that we had with the diversity antenna, remember? Which is a bit more convenient because it's got two antennas built into the same package. One's horizontal, one's vertical. But this assumes that we have two Yagi antennas right next to each other via a diversity receiver, which shares a slightly different orientation of the beam pattern. One horizontal, one vertical. So, you know, this is brilliant because, I mean, you know, no matter where we are in terms of the, you know, the orientation of the plane, you know, even if we're in a hard bank roll, you know, obviously the Yagi that happens to be mounted horizontally is getting that really nice cross-sectional area shared with the transmission of the plane, which in this instance is horizontal. And again, when we return back to forward flight, straight and level, we've got that, you know, we've got the shared, the vertical Yagi is doing all the work. So let's turn on the, we'll go back to the front view, let's turn on the, this is your plane here. So to compare, we've got the rubber ducky, which gets you to about here. However, the benefit is we can fly right behind ourselves if we want and we'll still be in range, assuming we're not too far away, omnidirectional. And then we have our diversity, sorry, our circular we'll do next, which we can get a little bit further. And remember, it's less sensitive to your orientation of the plane, so it's a little bit more of a consistent range. And then we have the diversity pattern, which gets us out to here. and again it's a pretty good field of view. It's a nice sort of midway balance. And then we have the Yagis, which will get us all the way out here. Now again, it doesn't really matter whether it's a Yagi or a panel type antenna that's high gain. If you were to take a 15 dB Yagi and a 15 dB patch antenna, you know, it's going to look pretty much the same. So it might, I mean, for example, if you, one of the sort of recommended setups really, if money was no object, would be to have two diversity systems, in which case you could have the best of all worlds. So like personally, my plan would be, let's say you would have a, we'll turn everything off. What you would do is you'd have a diversity receiver connected to two Yagis. Yeah, so you'd have your two Yagis, one's horizontal and one's vertical. In addition to that, you would also perhaps have a circularly polarized antenna, which would allow you to, in the close range flights, when you're coming back into land, you would always have a solid signal, even if you were, you know, coming on your final return through some trees, for example. I'm just going to flick back to the front view. So, for example, I've got a diversity receiver, and I also have an oracle connected to a single receiver. So the single receiver would have the circularly polarized 8 dB patch antenna, and the diversity receiver would have the two Yagis with linear polarization diversity, and then both of those two systems connected together via an oracle, which again will look at the best picture and select between the two. And that, I feel, would give you probably the best all-round performance, because you know, you've got that long range on the antenna tracker with your Yagis. So wherever you are in the sky, the antenna's going to follow you. And again, when you come into land, even if you happen to be out of the range of the field of view of the Yagis for a moment, the circular antenna is always going to be giving you maximum reception. So that's an overview of antennas, polarization, gain and patterns. I hope this video has been helpful to you, and again, it's just to help you sort of visualize the concept of the different types of antennas and how they interact, and perhaps give you some idea of perhaps the best setup for your own purposes.